This podcast is brought to you by the AlmaMAC and Scientific Canada. It was recorded on the traditional territories shared between the Haudenosaunee and Anishinaabe nations. Enjoy. I feel like I just butchered that again, even though
That's close enough.
we just had the conversation. Okay.
My research on light adaptation in the fish right now.
I'm sitting in a kiddie pool, actually. It's quite nice,
Oh, that would be great.
but it's
man.
not very professional. Hello and welcome. I'm Adam and you're listening to the AlmaMAC. This week I'm coming to you from the parallel universe in the Arctic that was reported on last year around this time. The whole parallel universe thing, it ended up being called out as fake and not real. And there's been some good articles that discussed how science communication and the public's trust in science can get hurt from these weird clickbaity titles, but wow, turns out that it's real. You'll have to forgive me, it's really hard to get anything out of this wormhole type thing, but hopefully Sawayra finds this before the next episode. Sawayra, if you get this, could you also... So can you do the interview for Thursday? And I'll try my best to be back, but I don't know how I got here, and I don't know if I'll be able to edit this one. So I don't know. This is really weird. Also, could you add something about how to give the how to give virtual presentations workshop Dr. Bandler is giving on February 18th? Oh no! Oh, hold on, I gotta go. Someone's coming.
Hey, what's going on, everybody? Thanks for tuning back to the AlmaMAC here on 93.3 CFMU or wherever you're listening to this podcast. My name is Sawayra West, and thank you so much for joining us on another Thursday to hear about another McMaster graduate students' research, what they do inside and outside of the lab, or nowadays inside and inside of the home. So let's jump right in. The AlmaMAC today, for today's episode, we are pleased to welcome a third-year PhD candidate, Pip Matharu, who is in the Department of Mathematics and Statistics. How are things going for you today, Pip?
Pretty good. How's everything with you?
It's good. As good as it can be, you know, just staying at home and getting all dressed up when you go to the grocery store. That's it. That's the only time. Well, Pip, why don't we just dive right in? Can you tell us a little bit about your research?
Yeah, so I'm a mathematician and I work with fluids, and in particular I work with turbulence. And I'm looking at some theoretical and computational problems that occur in turbulence. Sorry.
Oh, I was going to ask, yeah, so can you describe, I know before in our little pre-interview you were pointing to your background, so can you tell us a little bit about what turbulence is and maybe in the context that you study it?
Yeah, so for those of you who can watch, I have, some turbulent flows behind me, and, you might hear about turbulence whenever you're on an airplane, or you can actually visualize it really simply in your home. Since everyone's at home right now, by just kind of turning on your tap. So what you can do is, we have fluids around us all the time. And if you take your tap and you just open it up a little bit, you can kind of see that the flow is really nice and it's what's called laminar because there's not that much kind of velocity in it. But as soon as you crank that tap open and you see all the bubbles and it starts spurting and everything, that's whenever it becomes a turbulent flow. And essentially, turbulence is a flow that has, certain properties, mathematical properties and physical properties, but it's flows that we really don't understand. They're spatially and temporally very complex, and they're very difficult to kind of predict what's going on. And that's why they're such a interesting mathematical and physics problem. It's turbulence and fluids are kind of known as, quote unquote, the last unsolved problem of classical mechanics.
It's actually really interesting that you mentioned that because when I was doing some research for this interview, and I know you also told me about the equation, I might be saying it wrong, the Navier-Stokes equation.
Yep, that's right.
Is it true that that's one of the 7 unsolved mathematical problems, and that and it's like the Millennium I was going to say Millennium Development Goals, but and if you solve it, you get $1 million. Is that right?
Yeah. So at the turn of the millennium, the Clay Institute had decided there were 7 fundamental and important problems that we want to solve in mathematics. So proving existence and uniqueness of solutions for Navier-Stokes is one of the goals, and the goal is to solve these problems within 100 years. So we got about 80 years left, less than 80 years left to kind of solve the rest of these problems. But yeah, Navier-Stokes it's a very simplistic partial differential equation, and it can be easily derived from first principles. But and we've known it for a couple hundred years, but we still don't fully understand it. We want to understand the existence and uniqueness of solutions. Because when we have an equation, we'd like to have solutions and we would like them to be unique. And if we can't prove that, it kind of says, do we need a new model, or what's going on?
Right. And Pip, if we can also focus in on your research. So you talked to us a little bit about turbulence and saying how it's really unpredictable. So what is it that you do in your research? Are you trying to develop a model that can predict turbulence?
So yes and no. So the problem that I'm fundamentally working on is a computational problem for my main thesis project, which is, as I had mentioned, turbulence is spatially and temporally complex. So if we wanted to compute these with computers, we have to use a lot of data points, and we have to kind of, if we want to solve problems that we're interested in, whether it's a biologist using it for weather predictions, an engineer trying to develop, maybe cars or airplanes, you really have to use a lot of data points. And the problem is even with supercomputers, these simulations can take months, years or so, which we really don't want to wait for. So so with my work, there is something called a large eddy simulation, which is where you take the equations and you filter them. And that is, you only look at and you only compute the large scale components. So the stuff that dominates the flow of the system. And with that, what happens is that you run into something called a closure problem, where you have more unknowns than equations, and you can't solve for all your unknowns. So you have to substitute in some additional term into the equation to compensate for all the stuff that you've kind of truncated and thrown into the garbage. So all that smaller stuff that happens in the flows. And what I'm trying to do is that there's some hypothesis and there's some work that, a lot of work actually has been done in this field. And, kind of they came into use, in 1960 or so. But a lot of these models have been produced in a empirical sense, and I'm trying to add some mathematical rigor into this field. So I'm using a optimization-based scheme in order to optimally find the best closure model with a certain mathematical structure. And this will shed light on the fundamental performance limitations of these kind of models, and whether it's good or bad. It's good for the fluids community to understand, if we use these kind of models, this is the best you could do. Whether we can do it if we can match kind of the very accurate flows identically, or if the best you can do isn't that great, it still sheds light on kind of the field as a whole.
Okay, and if you can help me wrap my head around what it means to have the best closure model. So I think you were talking about it at the end, how that it can, would it be like the closure model which has the least number of unknowns, or that can be best applied to the particular problem? What would make a closure model good or the best?
Yeah, so that all depends on how we set up the problem itself. So it depends on at the end of the day, what I'm doing is an optimization problem. So it depends on how we define best. It could be we want things to match up in space, to be identical of the flow over these points in space over time, or we could define it to be if you're familiar maybe with Fourier space, which is a frequency space, we could say we want the frequencies to match over all time. It really depends on how we define best. And there are a number of diagnostic quantities that we test in order to kind of say, hey, this one looks really good, or no, this one's not performing that well. So we could look at the various types of energy. We could look at the correlation. We could look at kind of statistical structures and stuff like that.
And Pip, I'm really interested as a non-mathematics or stats graduate student. I'm really interested to know what this looks like, what your lab work looks like day to day, right? So you're talking about adding some sort of mathematical rigor to your work. For an individual that's not involved in this field, I'm just imagining you sitting, erasing a lot of equations on a piece of paper. So if you can speak to that a little bit, what kind of tools do you use for your work?
Yeah, so kind of sitting down, writing things on a piece of paper is pretty accurate. I also, I do a lot of coding. So I'm very fortunate. I'm one of the very fortunate grad students whose work hasn't detrimentally been affected by this pandemic, because I just need a pen, paper, and laptop and a good internet connection to really do my work. Some days I sit down and I try to work things out mathematically. And then once I get to a point where I can't do mathematics anymore, I transfer it over to the computer and then try to compute things and kind of go back and forth. It's kind of I would say maybe a 60-40 split. For 60% of the time I'm coding and debugging. And then 40% of the time I'm kind of doing math and reading and doing all that kind of stuff.
Okay, and Pip, I'm also really interested to learn about how you got interested and so passionate about this field, and kind of how you knew you wanted to pursue it and that graduate school was the right choice for you.
Okay. I will say, my academic career was a little non-linear in my undergrad. So
like that, still keeping the theme.
So I did my undergrad at Western. And I had went to Western for a very different field in kind of statistics and actuarial science. And I found out that I didn't really like that field. So I kind of explored a couple other things. I was at one point going to go into engineering, and then I eventually took a physics course for the first time in my life. And I fell in love with physics. And then I kind of found applied mathematics, and I ended up doing a degree in an undergrad degree in physics and applied mathematics. And through those courses, and through actually, I got to give credit to my professors at Western. They really inspired me to kind of keep learning, and I learned about numerical analysis, and I learned a little bit of optimization, and I learned about partial differential equations, and I thought that this stuff was cool, and this stuff is something that I would really like to look at. And one day I was kind of just chatting to some of the grad students at Western, and they just kind of said, "Why don't you do grad school? And there's great schools around, and you should." It'd be good for you. You seem like a computational person, so why don't you do some form of high performance computing? So I said, sure. And I started Googling, and eventually I found who is my supervisor now, Bartek Protas. And him and I sat down and had a conversation once I had actually applied to grad school. And he kind of told me, I read about some of his problems, and we sat down, had a conversation, and I kind of said, yeah, this is what I want to do.
Yeah, and Pip, it's so interesting how much, I guess, luck and serendipity is involved in our choices to go to grad school. Because it was a similar experience for me, right? Just kind of like talking with people and be like, oh yeah, okay, I guess I can do this. Yeah, I like learning. I like writing. Okay,
Yeah.
let's do this. Yeah. So I always find that interesting. I think also a really interesting thing too is how sometimes being a graduate student, you have to be comfortable with your research, perhaps taking some time to be transformed into policy, for instance, or perhaps not seeing those direct implications right away. Because I feel maybe in some other fields, like I'm in science, in some other fields, maybe you want to see that direct impact of your research right away. And we know that it takes some time, at least, if ever, it being transformed into policy or having certain implications.
Yeah, definitely. It's a very slow process, and that's for sure. And I'm sure you know that failures will come along the way, for sure. And it's all about, I find grad school is just about perseverance and kind of just sticking it out.
Yeah, exactly. Failures are so common, but I just feel like we only ever hear about the successes of people. And we only ever think about the failures of ourselves, but failures are very common. We just don't talk about it.
Yeah. I wish, sometimes I wish that there was I was talking to my supervisor about this recently. There was a journal of just failures, things that didn't work, because nobody talks about the failures, and it sucks. And especially in, today's world where we're all working from home, we can't see our office mates that, I know that I failed tons of times, and my office mates were like, don't worry about it. We've all been there before.
Yeah. Or like spending hours like trying to figure out the coding problems, seeing those red lines, the errors, and you're just like on Stats Exchange, like, why isn't this working?
Yeah, exactly.
Yeah. That's interesting, the point you bring up about the journal. I feel like I heard about something similar to that because I'm sure you're familiar with publication bias, the idea that only positive findings are published, whereas the null results or like studies that didn't find any effect aren't published. So I feel like there was a journal that might have been dedicated to that, but that could have also been something I dreamed. I don't know.
Interesting. I should kind of start Googling this after we're done here.
That'll definitely be my target journal. I'll say that. Yeah. Well, Pip, it was really interesting to learn about your research and really the computational side of things. And I'm happy I also learned a bit about how you actually do the work, because I at least wasn't fully aware of that when individuals who may be involved in math, stats, or physics, really like how their experiments or lab work plays out. So thanks for highlighting that for us. I am, however, also interested in things that you enjoy doing when you're not debugging or not erasing all your mathematical problems. So if you can speak to that a little bit. Yeah,
so I'm typically, I like to be a very active person. I go to the gym early in the morning. When I'm allowed to, I play soccer. I try to rock climb. I like biking, hiking, squash, tennis, any sport. I'll give it a shot. And then in addition to that, I also like working on cars. My dad owned a garage. So growing up, I kind of was always working in a garage. So it just has become a hobby now.
Okay, so I have one question for you, Pip. How worried should we be when the check engine sign comes on? Asking for a friend.
Does it make a noise?
No,
if the check engine.
It may or may not always turn on. Every time you turn on the car, it just always stays lit up, and you just pray and keep driving.
It might be something as simple as like one time you didn't tighten the gas cap enough, and that as a result, the check engine light has just stayed on forever. Or it could be something bad. I will say, if you ever see the check engine light flashing, don't risk it. Take it to a garage.
Okay, good to know. Getting some car
flashing.
Here.
Yeah, flashing is bad.
Okay, good to know. So do friends or colleagues come to you like asking about like if you really enjoy this, or is it just kind of like something on the side, or like you just kind of like tinker with cars?
Definitely friends who know me, and I guess anyone listening to this now. They give me a call whenever they're on the highway and they're like, "Hey,
Oh,
it's making this kind of noise. What should I do?" I definitely get that. It's been a while since I've actually physically worked on a car, but I definitely wouldn't be shy to get my hands dirty again.
nice. And I feel like staying at home has kind of forced some of us to either go back to the hobbies that we used to have or rediscover new ones. So hopefully that's given you an opportunity to do something like that.
Yeah, yeah, definitely. A lot of my hobbies have kind of been put off to the side due to the pandemic because you can't really do them. But there's hope on the horizon. So we'll see in the summer, maybe.
Yeah, we're optimistic, but maybe not too optimistic, but we're optimistic.
Yeah.
Okay, well, thank you so much, Pip, for coming on the show today. It was so wonderful learning about your really important work and also the things you enjoy doing, I guess, when you're inside your house. Maybe not outside yet. And thank you to...
Sorry. Thanks so much for having me.
Yeah, and thank you to all of you who are listening here on 93.3 CFMU or wherever you get this podcast from. It is appreciated. We will be back next week, as always, with another graduate student from McMaster, where you can learn about their work and things that they enjoy doing outside their lab. Thanks so much again, Pip.
Thanks.
Take care, everyone.
Hey everybody, it's Adam again. I think things are starting to clear up out here, and I'm starting to get a bit of a signal, so hopefully I'll be able to email out to Sawayra. I think she said she was going to be talking to some guy in the math department about Navier-Stokes, so hopefully you enjoyed that. I know I would. But maybe before we go, I can get Sawayra to play some of the interview I had with Dr. John Bandler about the workshop he's putting on. So, yeah, Sawayra, maybe if you can do that, that'd be great. Take it away. Obviously, things have got to change. So we've talked a lot about presentation skills and like how to get your point across, giving presentations in previous episodes, but that was always an in-person type thing. And well, we're not really doing that anymore. So the last time we spoke, it was off camera, but we were kind of throwing some ideas around, and you were telling me a lot about the things that you had been thinking of and working on. And I'm trying to employ one right now. I don't know if you've noticed a difference. I've raised my camera.
I know.
I've been staring into the black hole.
You are more or less looking into the camera. You're not quite looking into the camera. You're actually looking at the screen. So the camera is there, and I'm doing the same thing. It's human nature to look at a human being speaking. It's unnatural to look into the camera, which is where you really are. And I know that you're down here, but that's where you should be looking. So to me, coming back to I think the two most important things that I would think that are important for a virtual presentation of any kind is, what does your backdrop look like? And to be truly engaging, you really need to look into the camera. That means you have to forget what's here. You have to kind of convince yourself that's where your audience is. Now, it's easier if you have memorized. And of course, with 3-minute thesis, students have to memorize this. So once they've memorized, they can look into the camera. Or if you're speaking off the cuff like I am now, I'm still looking into the camera. Now I'm looking down at the screen where your image is. The other thing is the backdrop. It's preferable to have lines vertical behind you. Now, in my case, I have a couple of paintings on easels. And because they're on easels, it's normal that they may not be quite vertical. So really, I usually cringe when I see eminent people, prominent people with backdrops where they look like they're looking down at their laptop cameras. They're looking down like this, and the camera's looking up with strange perspectives at the back. It's distracting. And one of the things, if you notice when you look at TV talking heads, and we have a lot of TV talking heads now, and they're all virtual typically, you'll notice that the producers have clearly worked with those interviewees before they come on camera, and because lines are all incredibly, by coincidence, vertical.
Okay.
Almost entirely vertical, which means that, and that's clearly one of the things the producers want. It looks odd on a TV program with a bunch of talking heads, where some lines are doing this and some lines, unless it's deliberate, unless it's deliberately part of the backdrop. So you don't want it to be accidental. So having those vertical lines and remembering that what's in your backdrop becomes part of the impression that you're giving. And that's an indelible impression. It's hard to let that go. I definitely do not recommend virtual environments because of the strange glitches, and it looks kind of amateurish to do that. But that's the two issues. Look into the camera, vertical lines. And there's more, but I'll let you ask. Sorry, I'm doing a lot of talking here.
Yeah. So maybe we can... So first point one of the things, when you're presenting in real life, you're often talking about do you move around, and do you walk around, and how do you use your hands, and who do you look at in the audience?
Right.
Out the window. But we have a whole new set of things that we should be thinking about. So based on those two things that you were talking about, the sort of eye contact with the camera and the vertical lines, maybe we can do a little bit of a fix up of my camera. So let's just do an experiment. Right now I'm looking at the camera for anybody who's watching on YouTube. So I'm talking to you. This should look more normal, I think.
Right.
And this is me looking at Dr. Bandler on the screen.
Right.
So this feels normal for me, and it probably looks a little bit weird for viewers. Is that basically So here's another extreme. This is me looking over the camera if I maybe had some slides on the wall or something. Again, it's not really... I'm guessing you're feeling pretty weird about me staring into space like this. Is that right?
But not only that, Adam, imagine you were looking at you had dual monitors and you were looking over there, or in fact, the slides that you were presenting are there and the camera is over here, and you're constantly looking in this direction. That may be okay for private meetings where they're really intensely technical and so on, but you can't watch that. It's not human. If we were having coffee, if we were doing this over coffee, it would seem unnatural for you to be looking down at your coffee and for me to be looking down at my coffee, and we never make eye contact. I mean, we've evolved as humans to look into each other's eyes.
So here's a potential strategy that I was just thinking about. So I recently bought an attachment webcam, so I can move it around. So two ideas. One, maybe I can move it a little bit lower so that it's closer to where you show up on the screen. The other one, maybe I can just put little googly eyes on it and then pretend I'm speaking to the little camera guy.
Yeah. The other thing is, by the way, don't have yourself full screen. Just push the zoom window, for example, higher up so that it's a little closer to the camera.
Okay. Right. And so the other thing that you pointed out was the what's in the background and the vertical lines. So when I first set up my camera, I was kind of set up like this, which was not ideal.
No, it was
made me look like
it was much more extreme.
It's extreme, and I also am sort of a mythical creature at this point. It doesn't really work proper.
I know. Yeah, very good.
So
but anyway, there's lots more. There's lots more we can talk about on all this, and that's also the different. Let's think for a moment about in-person, virtual, and if you were doing a video. You're doing a video. Now, in person, you would walk around, you might, address someone over here, you address someone over there. If I were doing this right now, and I was sort of addressing somebody, you would know right away I was not looking at a human. I think we are keenly aware, I think through facial expressions or whatever, if there was really a person there, you would know that I was addressed. I mean, unless I was a really good actor, you would know if I were faking that there was somebody there that I was talking to.
Mm.
But in person, you walk around, you look at this person, you go that, it looks natural. Here we have a fixed stare in a particular point, and when we look around, when it's an in-person presentation like a workshop, or you do look people in the eyes.
So if you like that and you want to hear more, head over to scientificcanada.ca. Bye!